In this last series of videos here, we're going to be exploring the wave nature of light and what that means for us in optical devices. Since light is a wave, I figured the way to approach Young's experiment would be to do an analogous thing from the world of sound. So here is my sound analog. So you may have done this problem before when you were learning sound waves. You have two speakers and you're sitting over here somewhere. Well, let's make it not in the center. So you're sitting over here somewhere listening to the music, and of course, since you're a good physicist, you're listening to a wonderful rendition of tuning forks played at particular frequencies. And since you're sitting a little bit off axis, you notice that the sound you hear seems kind of muddy. In fact, you're having a hard time hearing anything at all, and you're wondering why that is. Well, you get to thinking about it a bit, and you realize, wait a minute, the difference in distance between these two sources here, L1, L2, might have something to do with it. If the waves are coming out in sync, if the extra distance that L1 has to travel is, say, an extra half of wavelength, then what will happen is that you'll have a crest coming in from L1 meeting up with a trough from L2 or vice versa. On the other hand, if you notice that this is a bright spot here, then you'd say, oh hey, this may be because the difference in wavelength, the difference in between L1 and L2 is either 0 wavelengths, 1, 2, 3. In either case, you have had crest meeting crest and trough meeting trough to have constructive interference. So just as a reminder here, our rule for constructive interference is that the absolute value of L1 minus L2 is equal to some integer times the wavelength. And for destructive interference, sorry about that. There we go. For destructive interference, our rule is that the absolute value of L1 minus L2 equal m plus a half times a wavelength. So certainly in the historic debate about whether light was a particle or a wave, if someone could construct an experiment that was analogous to this experiment that we can do with sound, then that would certainly be a compelling argument for the wave nature of light. And such an experiment was indeed concocted by a fellow by the name of Young. And I'm going to just apologize right now that I'm going to be butchering the artwork on this. And you may be saying to yourself, gee, is this the same Young as in Young's modulus? Yeah. And would this be the same Young who suggested that, at least in the case of proper names of foreign people, Egyptian hieroglyphics encoded sound values instead of the fashion held at the time of pure thought? And the answer would be yes, he got around. Anyway, in a modern construction, what you would do is you would shine a laser at a pair of slits that are very, very closely spaced together. There's no way I can draw this accurately. Either the slits are very thin, and you're looking down at this from above. The slits are very thin, and even the spacing is large-ish compared to the slits. but certainly still small compared to any other distance in the experiment. And so out over here to the right is a screen. And what you do is you'll notice that in certain areas, say if you sit right down the center, there's a bright spot. And thinking back to our analogy with sound, you say, well, maybe that isn't so surprising. After all, if you are right down the center line, then this distance L1 and this distance L2, they're equal. So that would satisfy our requirement that L1 minus L2 be some integer times lambda. In this case, the integer is 0. So you'll have, as the light travels from here by Huygens principle, since each of these spots here is a source of wavelets, this is acting just like the speakers in the sound analogy. And when we get out to the end over here, we have crest meeting crest, and then trough meeting trough, and so forth, ending up with constructive interference. Okay. And then if you go a little bit off axis, then let's look over here. You'll notice that there's, say, a bright band here and a bright band here. But then in between those, you'll notice that there's a reasonably dark region. And this is a continuously varying plane, to be clear. It's not quite as binary as I'm drawing it. But you look here at one of these dark zones, and you say to yourself, hey, it must be the case that the light coming from one of the slits is more or less canceling out with the light coming from the other slit. And that would indeed be correct. If we go and take a look, this is L1, this is L2. As I have it drawn here, we could observe that L2 is half a wavelength longer than L1. So that would again satisfy our criterion for destructive interference, that the absolute value of L1 minus L2 be equal to some integer plus 1/2 of a wavelength. In this case, again, the integer would be 0. So usually when we're giving names, and so similarly, if we look at the bright zone just past these first destructive minima here, we get more constructive maxima. So this usually gets called the central maximum and corresponds to when m is equal to 0. Then here, this would be called the first maximum, and it would be the first maximum on either side. That means that the difference in path length from one slit to that point on the screen versus the other slit to that point on the screen is one whole wavelength. And then we can keep going. We can have another destructive zone here, followed by another constructive zone here and here. Those would correspond to what we would call the second maxima, m equals 2, and so forth in both directions. So we can try to figure out what angles these would be at. So let's go ahead and draw a line right down the central axis. And let's say we're interested in the angle from the center of this to the first, sorry about that. Let me try drawing this a little better. From the center to the first constructive interference maximum. So there's a trick that we can do to get to this, and it'll be impossible for me to accurately draw this to any meaningful scale. So what we're going to do is we're going to zoom in really closely on our pair of slits. And we'll go ahead and say that the separation between the slits is a distance d. And the idea goes like this. If we go and take a look at a ray headed out to the mth maximum, the mth interference maximum, here are our two rays that are heading out to the screen eventually. However, the screen is probably several centimeters away, and the wavelengths of light are hundreds of nanometers, and the separation between slits is probably on the order of microns, or at least fractions of a millimeter. Either way, the distance between the slits and the wavelength of the light are both very small compared to how far away the screen is. So the trick that we can do then is to say that these two rays here that are heading off to the screen and will eventually intersect, for figuring it out, though, we can say that these are almost parallel. And this is just plain because the screen is so far away compared to the two slits. So to be clear, they're not parallel. They are going to intersect. They're going to intersect at the screen. But at any scale that you would attempt to draw this, there is no way that your eye could distinguish this apart from something that actually is parallel. So to approximate it, in order to get our angle here, so this angle off to the interference max on the screen, theta, we can then go ahead and say, well, this angle will be theta, that angle will be theta, and so forth. And then the idea here is going from here, from here to here, we drop a perpendicular. And this bit right here is the extra distance traveled, in this case from the lower slit. So if we're going to have a constructive interference, so we have a bright fringe, we need this extra distance right here to be equal to some integer times the wavelength of light. But what is this distance here? Well, this angle right here is theta as well. So this will be d times the sine of theta. Now, as a practical matter, the angles that we tend to deal with here are very small. Typically less than 1/10 of a radian or something like that. And if you remember from your calc, if your angles are small, so if your angles are small, the sine of theta, we can Taylor expand that out. That's theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus and plus and so forth. So if things are small, theta is already a small thing. Let's say it's 0.1. Theta cubed over 3 factorial, well, theta cubed will be 0.0001, and then you're going to divide it by 6. Theta to the 5th over 5 factorial, well, that's going to be 0.00001. And then you're going to divide that by 120. So if theta is small, these terms pass the first term and pretty much just say that they're almost 0. And then we can approximate that sine of theta is approximately theta itself. So a lot of times you'll see this relation written as the angle of the mth interference fringe is equal to m lambda over d. And here we are requiring that theta be in radians. So if you're given the angle in degrees and you're solving for the wavelength, say, or if you have the wavelength and they want the angle in degrees, it'll be on you to convert between radians and degrees. If you don't feel like doing that, and you can always go and use the more precise version here, where you just leave the sine theta as sine theta, but it isn't really going to matter for any practical experimental setup. So how will these fringes wind up being physically spaced? Okay. So if I go over here, there's my double slit. Way over here is my screen. So this is my mth maximum. So this is my angle theta m here. If this distance is L from the slits to the screen, and we say that this distance here is y sub m, well, okay, we can say that the tangent of theta m is equal to ym over L. Now, it turns out that, again, for as tiny as the angles are that we're dealing with, the sine of theta and tangent of theta are sine of theta and tangent of theta are basically equal, and they're both basically equal to theta. So if you just want to cheat it a little, you can go ahead and say that theta m is approximately ym over L. And then we can go ahead and put in what we had before here to get that, after rearranging that ym is equal to m lambda L over d. Alrighty. So, and this is so seeing this phenomenon could only happen if light was a wave. The experiment has been done many times, and sure enough, you see these exact interference fringes exactly where you would expect them. So this is, at least in principle, a way that you can measure the wavelength of light that you don't know. Alrighty. There's another application of this where we will have to be a little more careful. And that's called a diffraction grading. So in diffraction grading, instead of there being 2 slits, there's a gazillion slits. And all of these slits are separated by a distance d. And again, it's going to be the same deal. Way out over here somewhere is the screen, a very long distance L away. And it's going to be the same deal. You'll get out at the screen somewhere, you'll have a bright central fringe. Then you'll have bright fringes here at m equals 1 and so forth. But the difference is that the fringes will be very thin. In fact, we usually call them lines, to give you an idea. And they'll be separated by very large dark areas like so. And you'll also find that the spacing isn't uniform either, at least in a practical experiment. But again, it's the same idea. If you want to find the m equals 1 fringe, it'll turn out that it will be at the angle where if I look at two adjacent slits, say this slit here and this slit here, that this extra distance is equal to lambda. And similarly, if we did it over here, from here versus here, the extra distance would be 2 lambda. Okay, but then again, the same logic applies. In a practical experiment, these slits are ridiculously close, much closer than they are even in typical Young's experiments. Very close together. And so you can look at any adjacent pair and say that the rays are basically heading out parallel. Do the same trick we did with Young's experiment. But now the difference is that usually this spacing d in a typical diffraction grating is actually is on the order, it's only a little bit bigger than the wavelengths of light, maybe a factor of 10 or so. So it gets to the point where it matters what the separation is. And so you can't use the small angle approximations anymore. So every single pair of these acts like Young's experiment. They're all working in sync. The only difference is that you just plain have to leave it as d sine theta m equals m lambda and ym equals L tangent theta m, because in a real world experiment it turns out that the angles are big enough, because the spacing of the slits is small enough that the small angle approximations are no longer valid. So I also alluded that you have very thin lines with big dark spots. In a treatment beyond the scope of this course, you can argue that the maximum intensity for any particular for a peak here will go as the square of the number of slits illuminated times the intensity you would have if you just had a single pair of slits illuminated. But if you think about it, if you have n slits, you're only getting n times more light, but each peak is getting n squared brighter. So the energy for the light has to come from somewhere, and where it comes from is larger intervening areas of darkness. Now the practical application of this is spectroscopy. So in spectroscopy, say you cause some sort of transition in a molecule or something that you're studying, you can shine the light from that transition onto your grating, and then in the middle you'll have a central maximum, and there, because that's just right down the middle, all the colors will overlap there. But let's say you had a red line and a violet line, you would find that the the, the red line, because it has a longer wavelength, will diffract through a bigger angle than the violet line. So these are both m equals 1 here. But the reason that they're in different locations is because the wavelengths are different. So you can very, very precisely measure the wavelengths of the light because you know very precisely the construction details of the diffraction grating used. And you can measure the angles very precise. You can measure the angles quite precisely. With sufficiently clever material, material is possible to get parts per billion accuracy in some of these measurements. So by taking such precise spectra, what we find is that every atom has its own unique spectrum. Every isotope of every atom, and even every isomer of every molecule has a unique fingerprint of lines. And this fingerprint is due to the electron structures of the relevant atoms or molecules. And so this is what will allow people, when they have some sort of unknown substance that they're trying to analyze, they can get the spectrum from it and figure out what it is that they're looking at. Okay, next time we will take a look at thin film interference.